Okay, now we're going to distinguish between reversible and irreversible processes. So all the theory of thermodynamics that we have been working on is based on idealized reversible processes. And what do we mean by a process is idealized or it is reversible? Well, we mean the following. If we start with an initial state, P initial, V initial, and then we go to a final state, P final, V final, along some path X. And if I want to go back to the initial state from the final state, P final, V final goes back to P initial, V initial. If this can be established on the same path, so I can achieve this task on the same path X, then I'm going to call this process reversible. So, for example, if I plot here a pressure volume diagram, a certain path, so I start at this initial state, V initial, P initial, and then I go, let's say, on this path to V final, P final. And if I can go back to the original state following this path, or I can go from the initial state to the final state following this path, then this process becomes reversible. And as you can see, since I can show this on this PV diagram, pressure and volume are very well defined parameters throughout the process. That means along the path. So if I pick any point on this path, I can tell you exactly what the pressure and volume values are at this point. Or if I pick any other arbitrary point, I can tell you what they will be on this point. So these are very well defined. And therefore, because pressure and volume are well defined, the process can be represented by a PV diagram. And in fact, in all real processes, this is not possible. Pressure and volume throughout the process are ill-defined parameters. They are only well-defined at the initial and final points. Therefore, they cannot be shown on a PV diagram. And irreversible doesn't mean that you cannot go back to the initial state. You can go back to the initial state, but this has to be on a different path. It cannot be the same path you have taken from the initial state to the final state. And as I said, all real processes are irreversible. Therefore, reversible processes are idealized processes. However, if you want to experimentally approximate them, this can be done by using this quasi-static process. Quasi-static process means, you will remember, it's a process in which every single point throughout the process is kept to be an equilibrium point. And how do I achieve this? Here is one way. This is a compression of a gas inside a cylinder where I have insulating walls. So you can see that these walls are insulating, so there is no heat exchange with the environment. And however, the bottom contact, this one here, so this contact here with the energy reservoir, it's thermally conducting. Thermal contact is established. So if you have a thermal contact with an energy reservoir, you have the temperature fixed on this energy reservoir. It's T reservoir, and that is going to be also the temperature of your gas inside this cylinder, because you have a heat exchange between the energy reservoir and your gas. So you're allowing heat to flow in and out of this system by exchange with the kinetic energy exchange with the energy reservoir. And remember, energy reservoir is a system where we have very large heat capacity, so a finite amount of heat exchange will not change the temperature of the energy reservoir. However, it will fix the temperature of the gas. And the way I'm compressing this gas, I add sand particles, one sand particle at a time. I wait for the piston to come down and to get a very well-defined pressure and volume, and then I add one more sand particle. So I do this process very slowly, and so doing so I have very well-defined pressure and volume values at every single point. Every single point is an equilibrium point, and therefore this is a fixed temperature quasi-static isothermal compression process. This is approximately reversible. Now, if I look at a real process that is irreversible, for example, adiabatic free expansion. You will remember this process. I have a membrane, the gas is trapped under the membrane. There are insulating walls and there is vacuum on top of the membrane, and suddenly the membrane disappears. For example, it's suddenly pulled out through a tiny hole which is sealed instantly, something like that. So what happens? This gas, when this membrane is removed, will be basically expanding into the vacuum, right? With no force. So remember, there is no force, external force being applied here, and therefore the work done on the gas is zero. There is no heat exchange with the environment because I have insulating walls, so Q is zero. Therefore, from the first law of thermodynamics, the internal energy change is zero. Therefore, the temperature change is zero. So in this process, if I try to put these gas molecules back under this membrane and re-establish the initial conditions, it's impossible. Once it expands into the vacuum, it's impossible to expect that all of these gas molecules will follow exactly the same path and reconcentrate below the membrane. So therefore, it's an irreversible process because its Q is equal to zero, an adiabatic process, because the work done on it is zero, the force is zero, it's a free process, it's adiabatic free expansion, an irreversible process. In a reversible process, all forces must be conservative. There must be no mechanical energy being lost to internal energy, so that by friction. In the case of irreversible processes, we have friction, which is basically all real processes. They always have friction. And this theory of thermodynamics that we have been using is based on the ability to show processes on PV diagrams. Therefore, in a adiabatic reversible process, you have PV to gamma is a constant. However, in this adiabatic free expansion process, because it's irreversible, pressure and volume are not well defined, throughout the process, PV to gamma is not a constant. So this theory that we have developed only applies to reversible processes, idealized processes that can be approximated by doing the processes quasi-statically, very slowly and keeping the equilibrium conditions at all times.